class, and today we're going to talk about connected masses. We're going to use three examples to introduce the situation, but they're going to be closely related. So let's go ahead and get started with them. First example. Determine the acceleration of a 15 kilogram block that is pulled with a 49 Newton force to the right on a frictionless surface. Well, this one starts pretty usually. Box, it's 15 kilograms, and it's being pulled to the right with 49 newtons. Finding the acceleration here shouldn't be too hard because looking at the net force, there's only one force applied on this, the applied force. There's no friction to resist it or anything. So our net force being mass times acceleration would simply be 49 newtons, and the mass is 15 kilograms. So determining the acceleration should be pretty trivial. We see here that 15a, just divide both sides by 15, will get you a on its own. When you punch it into your calculator, that'll be 3.27. All right, let's look at our second example. This one was fairly easy. Example 2, 5 kilogram block. It's tied with a rope to a 10 kilogram block, and both are placed on a level frictionless surface. And the 5 kilogram block is pulled to the right with 49 newtons. Determine the acceleration of the block. Well, let's take a look. We have ourselves two blocks, and they're tied together with a rope. We have our 10 kilogram one and our 5 kilogram one. And again, we have a 49 Newton force applied to the right. When looking at the net force of this, we see that there's still only one force. There's just an applied force. But if we think about it, this is where things change. This is the mass times acceleration is 49 newtons. What's our mass this time? Are we pulling just the 5 kilogram block? Hopefully, you just said, no, Mr. Westergaard, we're not. Because you can see that the 5 kilogram block is attached to the 10 kilogram block. And if you pull the 5 kilogram block, you're also pulling the 10 kilogram block. Because they're connected by a rope, you're pulling both masses. So you'd have to combine both of those masses, both the 10 kilogram and the 5 kilogram, because you're pulling both of them. And we see here that this turns out to be the same thing as in example 1. That is very intentional. So you can see having two masses that are connected is the same thing as having one mass that's the same size of the two masses together. Now that is a bit of a simplification. We can make this a little more interesting by making them connected masses, but now we're going to change the way that they are sitting on the table. Let's take a look at example 3. We have a 5 kilogram block that's tied to a rope to a 10 kilogram block, and the 5 kilogram block is placed on a table, and a 5 kilogram block is hung off the edge of the table, and there's a frictionless pulley. Well, this is very different. So here's my table, and apparently there's a pulley on here, 10 kilogram block, and it's attached with a rope to our 5 kilogram block. Well, if I was looking at this, what forces are acting on these blocks? Well, I know my 5 kilogram block is definitely feeling some gravity. And you know, so would my 10 kilogram block. It would also be feeling some gravity. But my 10 kilogram block is on a table, it's on a surface, which means it experiences a little bit of normal force. And the rope pulls with a little tension, pulling that forward, but also pulls backward with that 5 kilogram block. Now, how do I deal with this? This looks far more complicated. Well, some things are nice and easy. See this normal force and gravity? They are going to balance out in this case. So we get to ignore them. And these tensions are internal forces within the rope. Internal forces are not outside forces. They don't accelerate the objects when you look at the whole picture. So we actually don't have to look at any of those. So if I was seeing, the only force that's left here is just the force of gravity on the 5 kilogram block. The net force is just the force of gravity on our 5 kilogram block. I'll call it FG5 to show that it's different from the force of gravity on the 10 kilogram block. Now thinking about this, is that 5 kilogram gravity, is that pulling just the 5 kilogram block? No, it's pulling both the 5 kilogram block and the 10 kilogram block because they are attached by a rope. Huh. So this means that when I'm dealing with my net force, the total mass, the mass is again the total mass between the two. It is 10 plus 5. We're pulling both the 10 kilogram and the 5 kilogram with that gravity. And that's multiplied by the force of gravity on a 5 kilogram block, which we know is 5 times 9.8. So we'll get 15 times A is equal to 49. Or again, we find the acceleration is going to be 3.27 meters per second squared. I deliberately chose all the values to make sure that they're all the same. To see that these are all related, even if they're looking a little different. Now, something is very different about this. What is the direction of motion? We can see the 10 kilogram block would slide to the right, and the 5 kilogram block would go down. What should I say for my acceleration? Okay, it says the problem says determine the acceleration of the 5 kilogram block. Okay, the 5 kilogram block is going to be accelerating 3.27 down. Good thing we read our question to make sure we know which direction it should go. Hopefully these 3 examples have shown you a little bit on how we can relate different situations when we're using ropes to connect different masses. So when you have masses that are connected, there are some things that you should do. 1, find the forces that act on each object and be clear in your free body diagram where each force goes. 2, you should solve for the net force as a system. The term system is the term that people commonly use to describe looking at the thing as a whole, looking at all of the parts. And 3, be careful with pulleys. Clear directions of up and down and right and left don't mean as much anymore. As we saw, pulling the 5 kilogram block down moves a 10 kilogram block to the right. Up, down, left, right don't mean as much. We are going to have to define a positive and negative direction that will bend because of pulleys. Our net force equation will be using forces that work in directions of motion, and it's all about who wins and who loses, what's working together and what's working apart. That's going to be all for today. We are going to try more examples of these connected masses throughout the week. See you later. Have a good day.